Here the Schrodinger wave equation is shown. It is well known to you, and now in classical as well as quantum physics, the total energy of a system, that means the summation of kinetic energy and potential energy, is called Hamiltonian. Suppose we have the total energy of a system is kinetic energy plus potential energy. As we know, the kinetic energy can be expressed as half mv square or p square by 2m, where p is the momentum and potential energy is Vx. V is a function of x, and h represents the Hamiltonian. Now if we substitute for the expression of momentum operator, which we have already derived, that is p is h cut by I del x, and substitute in the Hamiltonian function, the Hamiltonian operator is given by h cap is equal to minus h cut square by 2m del 2 del x2 plus Vx. Now in our later classes we shall discuss the time independent Schrodinger equation. Well, it is clear that this Hamiltonian operator working over its eigenfunction gives us the total energy of the system. Then energy observable is associated with the Hamiltonian operator. We have already discussed that Schrodinger equation plays the central role in case of quantum mechanics. The equation is minus h cut square by 2m del 2 psi, and here the psi is in uppercase, del 2 psi xt del x2 plus Vx psi xt. This is equal to I h cut del psi xt del t, where we know that psi xt is called the wave function. This is the wave function, and Vx is the potential energy of the system, and h cut is nothing but the Planck constant divided by 2 pi, and I is root over of minus 1. So this is this differential equation is to be solved to obtain the value of psi. Now here we have assumed that v is the only function of position coordinate. It is independent of time. And now here it is a partial differential equation. We shall first use the method which we call the separation of variable technique. Separation of variable. To treat this partial differential equation, as we have seen that psi xt is a function of both position and time, let us assume it is uppercase psi. Now let us assume this is a simple product of two functions. This psi is in the lower case, it is psi, and phi as a function of t only. Look here, psi xt is a function of both position and time. It is a simple product of two functions where psi is only a function of position x and phi is only a function of time. Now using this we shall treat this equation. Now from here we are going to obtain the value of del psi del t. Now from this is called number 2 and this is number 1. Now from number 2 we have del psi xt del t. Look here, when we are going to take the derivative with respect to time, psi is only a function of x, so it will not be affected, and we can treat it as a constant term. So it will be psi x and d phi dt, because phi is only the function of time, psi is only a function of x. So we have this one, and del psi xt del x. When we are going to take differentiation with respect to x, then phi t being a function of time, it appears as a constant. So we have phi t d psi x dx, and we can again, if we take the derivative, del 2 psi xt del x2 Again, phi t being a function of time, it is constant. So phi t d2 psi x dx2. So we have this one, call it number 3 and call it number 4. And now if we put these two values in the equation, first equation, we have minus h cut square divided by 2m del 2 psi xt del x2. This is uppercase psi. Del 2 psi del x2, we have obtained the value, it is phi t d2 psi x dx2 plus vx, and what is psi xt? It is psi x into phi t. This is equal to I h cut del t of psi xt. This is equal to, from number 3, we have psi x d phi t dt. Then if we rearrange this equation, we have I h cut psi d phi dt minus h cut square by 2 phi t d2 psi x dx2 plus vx psi x phi t. Now divide this equation in both sides by psi x phi t. Divide this equation. So we have minus h cut square by 2 phi t cancels out. We have psi x d2 psi x dx2 plus vx. This is equal to I h cut psi x cancel out, 1 by phi t d phi t dt. What we have performed, we just divide this equation by psi x phi t. Just divide this equation. And look here, in the left hand side we have minus h cut square by 2 1 by psi x d2 psi x dx2 plus vx. Look here, all are function of x. And this is equal to I h cut 1 by phi t d phi t dt. Here this is a function of time. Now this is a function of time in the right hand side, and in the left hand side this is a function of x alone. And we also already assume that v is only a function of x. So left hand side is only a function of x and right hand side is only a function of time. When it is possible, this is only possible when both sides are constant. Okay. Only it is possible when when the left hand side is a function of x, right hand side is a function of time, and they are equal. When it is possible, when they are constant. Now let us suppose this equal to this is equal to some constant e. Okay, so this is E, and this E represents the energy of the system. We are taking the separation constant as E. This appears as the energy of the system. Now here from the left hand side, if we take the left hand side, this is equal to minus h cut square by 2 1 by psi x d2 psi x dx2 plus vx. This is equal to E, because this equal to E. Now just by some rearrangement of this equation, we have minus h cut square by 2 d2 psi x dx2 plus multiplying through psi x. This is equal to E psi x. So look here, our partial differential equation, the Schrodinger equation, which was a function of psi xt, here it is only a function of x. Here, look here, this equation turns into an ordinary differential equation. By, if we have the knowledge of the potential of the system, we can obtain the solution of this equation, and this is called the time independent Schrodinger equation. And by solving this equation, we can obtain psi x. Okay. So differential equation, again we have from the left right hand side I h cut 1 by phi t d phi t dt, this is equal to E. Look here, this is again straightforward, it is d phi t by phi t minus I e by h cut, just taking here dt, and if we integrate it in both sides, we have this is ln phi, and it is minus I e t by h cut, and from here we can obtain that phi t is going like e to the power minus I e t by h cut, where there will be some constant multiplied with this function. This is giving us, this part of this equation giving us phi t. So from here we can obtain phi t. Psi x is already determined. So from our assumption, the complete solution of this equation, it was psi xt, it will be psi x into phi t, it will be psi x, and phi t is e to the power minus I e t by h cut. So look here, Schrodinger equation, which equation was a partial differential equation, by adopting the separation of variable technique, assuming psi as a function of capital psi as a function of both position and time, we assume it as a function of only x and time, and using separation of variable we convert this partial differential equation into two ordinary differential equation. This is the x dependent equation and this is the time dependent part, and by solving this we can obtain phi t, and if we have the knowledge of the potential energy of the system, of the potential of the system, we can obtain the expression for psi as a function of x. Then the complete solution can be obtained by psi xt, psi x e to the power minus I e t by h cut, and the general solution will be a linear combination of the separable solution. That is, we can write it is starting from n equal to 1, it will be Cn. Cn is these are the arbitrary constant, psi nx e to the power minus I e n t by h cut. So by this method we can obtain the solution for the Schrodinger equation.